Hello, and welcome to the last part of Chapter 15, Acid and Base Equilibrium for AP Chemistry. I figure that we didn't get through much in class yesterday, so we better just record the end of this video so we can spend all our time calculating these titrations. So this will be the last part of your notes. First of all, let's do a quick little check for understanding. What are we looking at here? We're looking at a titration curve, and it has some different letters here to help us answer the questions. First of all, which type of titration is represented here? What that means is a strong acid, strong base, weak acid, strong base, or strong acid, weak base. So first of all, we should look at our axis here that says we added sodium hydroxide. If you remember, that's a strong base, so I have to have something with a strong base. So is it a weak acid or a strong acid? Well, if it's a strong acid, it would be below a pH of 1, and my equivalence point would be at 7. That's not happening in either area, so it's a weak acid, strong base reaction. That's my answer to number 1. Number 2 wants to know which one's the equivalence point. Well, remember, equivalence point is the middle of that upward line, and C is right about there where my pH is going to be 8-ish. It also says for number 3, what's the point where pH will be equal to pKa, or it will be around its best equilibrium point for Ka? Well, that's going to be in my buffering zone here, so around A or B would both be acceptable answers for that. A is probably a better answer to where that equilibrium point will lie. And number 4 says, what's the point where the solution's most basic? Well, that's definitely up here at D. That's a pretty easy one. Number 5 says, at this point, the solution is buffered. Well, remember our buffering zone is where it levels off here for us. So once again, I would accept A or B, but B is a better answer. All right, so here's just a little reminder of what all our different areas are on our titration curve. And on this one, this is a strong acid, strong base titration curve. And it's going to remind us how to calculate. If we're at the beginning, all we do is a negative log of H plus to get our pH, and we're talking strong acid, strong base here. If we're in our buffering zone, we have to do that stoichiometry. And then our shortcut, if we're at the equivalence point, our pH is going to be 7. And if we're up here, we need to do some more stoichiometry to figure out our pH. It's almost the same for a weak acid, strong base or a strong acid, weak base, except at the beginning we have to do an icebox. Here we're going to do stoichiometry. In the middle, we're going to do an icebox. And up here, we're going to do some stoichiometry. Okay, so let's talk about indicators for a minute. We remember that indicators are something that change color when they're in acid-base solutions in order to help us figure out the equivalence point. And, the way we determine the approximate equivalence point, there's essentially 2 options. We either graph the titration curve using a pH meter, which is like what we did when BioNetwork visited, and we would see that sharp increase or drop in pH that tells us the equivalence point. But if you don't have that fancy stuff, then what we would do, like in our lab, is add an acid-base indicator. But we have to pick the right one, okay? The one that's going to mark the endpoint of a titration by changing our color. Now there's a difference between endpoint and equivalence point, and we've talked about that. The equivalence point of a titration is not necessarily the same as the endpoint. The equivalence point is stoichiometry by, pointing it out by numbers, the perfect point where everything's equal. And the endpoint is where the indicator changes color. These don't match up, but they're close, but they don't match up. If we make sure we pick the perfect indicator, we can get these really close and, negate some of our error. So typically indicators are weak acids that change color depending on whether one little H plus proton is present or absent. And the general reaction that occurs here would be represented by this. We have a hydrogen attached to an indicator, and what it's doing is it's reacting in solution to break off an H plus ion and leave behind whatever our indicator is as a leftover salt or a conjugate base. We can calculate the Ka of these guys just like we do all other Kas by putting our products on top and our reactants on the bottom. So this is one we're very familiar with, and when I do my magic picture, I use my phenolphthalein. It indicates around a pH of 10 for a base. And here are some structural pictures of it. So this is when it's colorless. That was when I said it was water in my picture. And this is when it turned pink. Take a close look and see what changed here. It's pretty hard to pick up the change, but the only thing that happened is one little H is missing, okay, from my OHs up here. One little H broke off and got let loose into solution. It doesn't take a big change for that color to occur. Now, in a titration of an acid with a base, the color change occurs when about 1/10 of that indicator is converted, or when 1/10 of it releases its hydrogen ions. And we can represent that by saying, this should actually be over here. I'm at my home computer and it's throwing my slideshow off a little, but when my indicator conjugate base is over my entire indicator, it should equal about 0.1 if I were to compare those concentrations. And we can determine that pH by plugging those guys in as 1/10 in the equilibrium equation. We can determine that exact pH where the indicator color change will occur, and I'll show you an example. If it's a base with an acid, all we did was flip it around and put our entire equation on top and our indicator on the bottom. And that's the same reason that we have to flip around our equations when we did those weak acid strong base titrations as well. Okay, so here's an example. Brothymol blue, which we've worked with before, is an indicator with a Ka value of 1 × 10 to the -7. It's yellow in its HLN form. So that is its, I keep calling it an L, but it's an I. It's HIN form. That is when it hasn't released its hydrogen, so that's how we get it out of the bottle, essentially. And it's blue when it's in its ion form. So if we put a few drops of this indicator in a strongly acidic solution, and then we titrate the solution with NaOH, we want to know what pH the indicator color change will first be visible. Well, we're going to use that 1/10 that we talked about. So here's what it would look like since we talked about before what our Ka would be. And we're just going to put our Ka over here, and we're going to plug in that 1/10 we talked about and solve for H. And when we solve for H, we're going to get out 1 × 10 to the -6, then convert that to a pH by doing our negative log. So at a pH of about 6, this indicator is going to change color. If we knew we were doing a titration that would change around 6, we would choose this indicator as our best option. Okay, so we can actually use that shortcut that we talked about to determine the pH when an indicator changes as well. All we do is put our conjugate base over our acid like we're used to and plug everything in there. And we would assume that that color change is visible when it's 1/10. So if we're plugging that in, then the only thing that's really coming into play here is our negative log of our Ka. So essentially we take our negative log of our Ka and subtract 1 from it, and that will tell us what our pH is going to be where that color change occurs. So that's 2 different ways we can do that calculation. Now, what if it was a base? If we had a basic solution and we were titrating with an acid, that color change was reversed, okay? It was still visible when 1/10 switched or was converted, but we flipped our 1/10 around, and now we have our compound on the bottom and our ion on top. So the only thing that would change here is instead of subtracting 1, we're adding 1 when we use our shortcut. So in general, what's that tell us? That tells us that the color change for an indicator occurs 1 above or 1 below of our negative log of our Ka. Here's just a good little diagram that shows the different types of indicators. So if you were going to consider doing a reaction that would change around 6, okay, I would go up here to 6 and come down and see what's going to indicate a color change around 6. Now, your initial when you go across is methyl red. That's actually not a good one to choose because it would already be yellow down here. So that wouldn't give us a very good indicator of where our equivalence point would be. But look at this guy. Irochrome black tea is a pretty good choice, and it changes right around 6. Brocesterol purple, probably not, changes a little early. Perhaps our alizarin, it changes at a good spot. And our brothiamol blue, probably not a good choice since the change doesn't really start until a little later. There are some unique ones though. Look at these guys. They change in 2 different places. And if you remember when we did our precipitate lab, I told you there were some indicators that changed in 2 different places. It's really interesting to see the color change and then see it change to a secondary color, or like this one, the color changes yellow and then it turns back. So really interesting changes here that occur with these indicators. And remember, they're usually some sort of weak acid that's letting go of a hydrogen. So when we choose an indicator, we want that endpoint and the titration equivalence point to be as close as possible. This dramatic change in pH makes it easier to choose that indicator because really one single drop will change it. A question you can see on the AP exam about this would be like, what's the best indicator to choose for this reaction? And it doesn't mean that you have to memorize where the indicators change. You just have to be able to look at a chart and understand the best indicator to choose, and that might be a chart that provides you with some Kas, so you need to either do the negative log of that Ka and add 1, or subtract 1, depending on whether it's a base or an acid solution that they're talking about. Here's just a good little diagram for you about 2 of the indicators, and this is a titration curve of our strong acid, strong base, and what it's saying is this equivalence point's right in the middle. Which one would you really want to pick here, methyl red or phenolphthalein? Well, we really often use phenolphthalein, but really if we chose that, it would be past the equivalence point. It's probably better to be past it than before it though, because our methyl red would have been way before it. Hopefully there's something better there we could choose if we needed to get a more exact equivalence point on that. Now here's one when we have a titration of HC2H3O2. What is that? Vinegar, acetic acid, and we're reacting with an AOH. So weak acid, strong base, that equivalence point shifts upward. Perfect for phenolphthalein because it's going to make that change right at the equivalence point, which would be just perfect. All right, well that's that. I will see you soon, and this was Unit 15 Acid-Base Equilibria, the final video.